Chapter 11, Streams and Floods. In this chapter, we will talk about humans and rivers, the hydrologic cycle, drainage networks and patterns, the factors affecting stream flow, the work of streams, floods, and flood control. We'll start with humans and rivers. What's going on here? And what does it have to do with streams and floods? A stream is any flow of water through a channel defined by its banks from the smallest creek to the largest river. The Nile River Basin. The Nile River is 6,825 kilometers long and it drops 1,800 meters in elevation from its source to its mouth. It flows from the Burundi to the Mediterranean Sea, covering 35 degrees of latitude. Egypt became one of the earliest sites of civilization because of the Nile. Humans began diverting water from the Nile for irrigation over 5,000 years ago. The pyramids were built during the time of ample water in the Nile. The history of the Nile illustrates how organisms in the vicinity of a stream can be placed under considerable stress when significant changes occur in stream systems. We tend to take streams and rivers for granted, but they perform many positive functions in today's society. They bring water to irrigate crops, they provide drinking water, supplies coolant for power plants, transportation, it provides ecosystems for wildlife, recreation sites. The hydrologic cycle: water evaporates from the oceans, rises through the atmosphere, condenses to form clouds, is then released as precipitation that may flow over land in streams, sink underground, or be absorbed in plants. And no, it doesn't necessarily go in that order. That's just generally the way that the cycle goes. The vast majority of Earth's water is in the oceans. About 97% of it's there. Only about 3% is on land. Where do streams come from? Many, such as the Colorado River shown on the left, come from small streams on the slopes of mountains. Their source water can be snowmelt from the mountains or rainwater running off the slopes. The source of the mighty Mississippi is a small lake in Minnesota. Rivers often come together to form another river. In the image on the right, these two rivers join to form the Ohio River in Pittsburgh. The majority of precipitation on land runs off to the oceans in the streams. On average, the length of time that a given volume of water remains in streams is about 14 days. Only a small amount of precipitation on land sinks into the ground, as infiltration rates are slow compared to runoff rates. However, the volume of water stored in groundwater is 70 times greater than the volume of water in the streams and lakes. Ice stores about 3 times the volume of water found in groundwater. Many rivers have sources in glacial melt water. For example, the Brahmaputra or the Ganges. Regardless of where or how they start, streams always flow downslope. They often join other streams to form a network. They empty into another body of water, another stream, a lake, an ocean, a reservoir, a wetland. This lowest point to which a stream flows is called the base level. What controls the amount of water in a stream channel? Well, the size of the area it drains and the average precipitation over the area. The Nile and the Mississippi have the largest drainage basins, each covering over 1 million square miles. There are patterns to these drainage networks. The drainage basin is the area drained by a stream and its smaller streams or tributaries. Above, the Mississippi drainage basin is composed of several smaller drainage basins, which are the colored areas. It takes up half the land area in the United States. It's a pretty big area. There's a close-up of the network and patterns of the drainage area. Drainage networks and patterns. These are the different types of patterns that are found. The dendritic drainage patterns, named after the dendrites in your brain. These are characteristic of areas where the geology is relatively uniform. The trellis patterns are found in areas of weak and resistant rocks. The third one down, the rectangular patterns, occur in regions where the streams are controlled by joints, fractures in the underlying bedrock. And radial patterns are typically found on the flanks of volcanoes, where streams flow downhill from the summit. There are several factors that affect stream flow. The gradient, or the slope of a stream. It is the change in elevation of the stream over a horizontal distance. Where is the stream's gradient the highest? Near the headwaters or near the mouth? How might the features you see in this picture compare to what you would observe in a low gradient river? Rocky banks and channel. As you continue downstream, a channel becomes less rock, changing to gravel, and then sand, and eventually fine-grained silt and mud. That would be the channel roughness. Which would you expect to flow faster, the high gradient part of a stream or the low gradient part? Why? Which of the three streams, A, B, or C, shown here would have the highest stream velocity? And why do you think that? Cross-sectional area and hydraulic radius affect the rates of flow. The wetted perimeter equals the length of the surface of the channel banks and bed in contact with the water. A large cross-sectional area compared to wetted perimeter is large hydraulic radius and therefore a relatively high stream velocity. The higher hydraulic radius, the higher the velocity. Downstream, channel roughness is generally reduced and hydraulic radius increases. Therefore, stream velocity increases downstream. Stream discharge is volume of water that passes a given point in 1 second. How much passes 1 point in 1 second? 50 million gallons of water discharge into the Atlantic Ocean from the Amazon River every second. 50 million gallons. That's a lot of water. All streams erode particles from channel beds and banks and then carry them downstream. In this one, at the top, This is about 5 months after the eruption of Mount St. Helens. This channel of the Upper Muddy River had formed in the soft erupted materials. Here, note the increase in the width and depth of the channel 12 months later. Same place. Just a little bit of change there, and it only took 12 months for that change to occur. Water is very powerful. Erosion produces stream load, which is the combination of bed load, suspended load, and dissolved load. How is stream color affected by load? The suspended load increases when discharge increases. The higher the velocity, the more energy there is to move the particles. The Amazon River has 10 times the discharge of the Mississippi, but it carries only 3 times the load. Why might this be? What factors account for this difference? Well, the source materials are different. The soils with different characteristics, different weathering histories of the two regions. The area of the Amazon is much more densely vegetated. Vegetation protects the underlying soil from erosion. The Rio Negro and the Rio Solimões rivers converge to form the Amazon River. Note the difference in the sediment load between the two rivers that give them different colors. Load versus discharge. This will be the discharge along here, and this is the load. The Yellow River in China carries the highest sediment load relative to discharge of any river in the world. That's why it's not very transparent. And you can see why they call it the Yellow River. It has that yellow tint to it because of the types of soil that are eroded into it. Here's a braided channel in Alaska. Note that it's coming off this glacier and it's melting. As a stream flows down, it drops some of its load. The heavier particles drop out first. When a stream has a heavy load, sediment is often deposited in the stream channel itself to form bars or islands. These deposits split the channel into smaller channels, forming a braided channel. The work of streams. Maximum velocity is here at the top. Remember that velocity includes speed and direction. Minimum velocity would be here at A, slows down in this area where it continues to go around maximum velocity on this side. It goes faster around the outside of the curves than it does on the inside. Stream velocity varies across the width of the channel. Stream velocity is greatest in deeper parts of the stream and along the outer banks of the channel on the outside of the curves. Stream velocity is lower in the shallow parts of the channel and along the inner bank. As a meander becomes larger the channel migrates across the floodplain in the direction of the erosion. Meanders is broad curves in a stream. Velocity of the stream varies as it moves through these large bends. On the left side, the channel migration in the Memore River. You can see the red and the white here, how much it's changed over time. And in the right-hand side, it shows the creation of an oxbow lake. Rivers dump a lot of their sediment, and it forms a delta where they enter the relatively quiet waters of an ocean or lake. The velocity rapidly declines as the river hits the ocean, causing the drop of the sediment. This is the Mississippi River Delta. There's constant dredging required in order for ocean-going ships to navigate the main river channel. A flood is a temporary overflow of a river onto adjacent lands not normally covered by water. Floods usually occur when the amount of water on the land surface exceeds the volume of water that can be transported in stream channels and absorbed into the surrounding soil. Flooding is caused or influenced by magnitude, timing, and type of precipitation, human modifications of the physical landscape, the capability of the ground to absorb water, evaporation rates, and the physical characteristics of the stream system. On the left, you can see a graph of monthly rainfall for Cedar Rapids, Iowa. On the right, the distribution and magnitude of precipitation associated with a single storm over southern Iowa, July 4th and 5th. One storm. The most common cause of flooding is excess precipitation. In 1993, the Mississippi River flood was caused by both long-term and short-term precipitation. January through July, several Midwestern states received over 150% of their normal precipitation. It's a lot of rain. Heavy storms added large amounts of rainfall all at one time. This was spatially the largest flood in the United States history. It covered 44,000 square kilometers, or 17,000 square miles. In the arid southwestern states, floods occur because channels often have no surface water in them most of the year, and brief, intense storms cause flash floods. The soil simply cannot absorb the water quickly enough. In areas with lots of snow and ice, floods occur when temperature rises sufficiently to cause rapid snowmelt. When streams of snowmelt flow from warmer to colder regions, ice jams can form, blocking flow and making the flooding worse. Here's an ice jam along the Red River in North Dakota. The ice blocked the flow, backing up the river and forming a temporary lake. How do humans influence flooding? By paving covers or altering natural surfaces that otherwise might absorb water, by storm sewers that divert water from surfaces to dump it into natural streams, causing the streams to flood, by building housing developments or agricultural fields to replace natural wetlands, which act as water storage reservoirs, and the collapse of constructed dams. We can assess the potential of a stream to flood. Stream gauges measure the stream stage, the depth of water in a channel relative to a starting point for measurement. The data from most stream gauges become available via satellite for scientists. The USGS has over 7,000 stream gauges across the United States. You know, the time between the precipitation occurrence and the flood can vary. It depends on how close the precipitation is to the stream and how quickly the precipitation has fallen. For instance, let's say that 10 inches fell in the past 12 hours. Well, how far away was that from the river? How long will it take for the water to arrive to the stream? It depends. It could take a day or so before the flooding begins. Stage and discharge relationships for the river in Akron, Ohio, for the stream gauge in figure 1126. That would be this one right here. There's a stream gauge. Look, here's where they have the gauge. Check out the height of the water here and here. A lot lower in this photograph on the right than it is on the left. The hydrograph for this river in Akron, Ohio. The graph shows the stage measurements for the gauging station. The red arrows show the measurements for these, for the B and C, the high and the low. The U.S. stream discharge information is available online at this web address. The historical flood information can be used to determine how frequently flooding has occurred in the past and to estimate the likelihood of future floods. Historical discharge data is arranged in order from the largest flood discharge to the smallest, assigned a rank based on size and graphed. Recurrence interval is the average time in years between floods of the same size. Scientists can use graphs of maximum stream discharge versus recurrence interval to estimate the discharge of 100-year floods. An analysis of flood data in metropolitan areas over the last century suggests that floods caused by similar volumes of precipitation are actually larger and more devastating today than in the past. Despite advances in flood monitoring, provides some potential explanation for this apparent paradox. Why is it worse now than it was in the past? The city of Des Moines, Iowa. It was inundated by floodwaters. A corn crop in Missouri destroyed by flooding. Cities located on floodplains suffer the most economic losses. Floodwaters can carry contaminated water, contaminated with sewage and agricultural chemicals. Roads get submerged and have to be closed and repaired after the flood. Farmland is submerged. Production falls. Prices for that particular crop increases. Floods can deposit thick layers of sediment where it should not be. It can halt barge traffic for months. People die and are uprooted and evacuated. In the year 2000, 700 people were killed by the floods in the Limpopo River drainage basin in Mozambique. On the left, the river during a normal year. And on the right, during the floods, the width of the river swelled to more than 80 miles in some locations. We can try to stop floods, which is prevention, or we could adjust our lifestyle to deal with them effectively, which is adjustment. So stopping is the prevention, and just dealing with it, adjusting our lifestyle, is the adjustment. Artificial levees are raised embankments along a stream channel constructed to protect neighboring lands from rising floodwaters. A levee in West Virginia, on the bottom, protects homes from potential flooding of the Potomac River. Levees and flood walls protect cities and fields in a floodplain. Would this be prevention or adjustment? Flood control. Winnipeg. This will be in Canada. A floodway is a diversion channel that will transport floodwaters away from inhabited areas. Approximately 500,000 people live at the confluence of the Assiniboine and the Red River in Winnipeg, Manitoba, Canada. Is this an example of a prevention or an adjustment? Are they trying to stop it, or are they trying to adjust to the inevitability that it's going to happen? Wilson Lake Dam in central Kansas. Dams are used for flood control under the premise that floodwaters can be stored in the reservoirs to be released slowly when the threat of flooding has receded. Is this a prevention or an adjustment? What's the potential problem with this? Well, the storage facility must be big enough to accommodate the excess. Examples of adjustment tactics. Relocate the settlement to higher ground. Sales tax increases to fund projects that modify land use patterns in floodplains. The restoration of wetlands along riverbanks. Avoid development in areas prone to flooding. FEMA created to provide financial assistance to those affected by natural disasters, including floods. This concludes Chapter 11.